Okay, so as we talked about previously, if the path length difference is equal to half a wavelength, I'm going to get destructive interference at this point, and that means I'm going to get a dark spot. On the other hand, let's consider what happens if that path length difference equals one full wavelength. So I'll just draw the two beams, or these are sometimes called rays of light coming out from the two slits. So if there's a full wavelength difference, then the situation would be like this. Here's the wave coming from the top, and here would be the wave coming from the bottom. And you can see that because there's a full wavelength difference, they're in phase. So if d sine theta equals lambda, I get constructive interference. And in fact, you can, I think, see if this path length difference were 2 times lambda or 3 times lambda, you'd also get constructive interference. So this gives us our equation for the angles of the maxima of brightness on the screen, which is d sine theta, our path length difference, is equal to m times lambda, where m is any integer. So it could be 0, which would correspond to the straight ahead direction, or plus or minus 1. So let's say if we've got a one wavelength path difference, then this would be the m equals 1 up here, but down below an equivalent amount, there would be m equals minus 1. M equals minus 1, where the path length for the top one was longer than the path length from the bottom one by 1 wavelength. Or it could differ by 2 wavelengths, etc. So let's think about what the pattern of brightness and darkness that we would observe on the screen would look like. So straighten out the paper. So again, here's our barrier. Here's our observation screen. And I'm going to plot, let's maybe plot it in red, the intensity that's observed on the screen. So in the straight ahead direction, we would have a maximum in the intensity, and then it's going to fall off, and there'll be a minimum where we get destructive interference, and then it'll rise to the maximum. So that's where m is equal to 1. Here's m equals 0. Falls down, rises back up. I'm running out of paper, but that's where m equals 2. And similarly, down here, you'd have your m equals minus 1. Whoops. M equals minus 1 would be at this point. M equals minus 1. And if I keep on going, I'd get to m equals minus 2 down here. So what I have, and we could maybe call this point the m equals 1/2 angle. That's the angle where we first get destructive interference. This is the so-called ideal two-slit pattern, and it is achieved only when the slits are very narrow compared to the wavelength of the light that you're using.